I will start the presentation on the topic design of a 1.2 kilowatt single-phase bidirectional onboard charger for electronic vehicle and implementation of vehicle-to-load. Our project is focused on the design and implementation of a 1.2 kilowatt single-phase bidirectional onboard charger for electronic vehicle. The goal is to realize bidirectional power conversion, including the vehicle-to-load function. We emphasize achieving high efficiency, reducing input current throughput, and harmonic to improve power quality, and finally, ensuring reliable operation through robust control design and waveform validation. This image shows the overall topology of the OBC. The front stage uses an interleaved totem pole PFC based on the DC-link capacitor. And the rear stage used a dual active bridge DAC converter topology. The PFT stage controlled the output at 200 voltage to charge the DC-link capacitor, which feeds the DAC converter. The output voltage is controlled from 150 volt to 210 volt in 10 volt steps, completing the 1.2 kilowatt class OBC. The PFC and DAP are controlled at 20 kHz and 80 kHz respectively. The table lists the equipment used, circuit parameters, MOSFETs, and gate drivers. This illustrates the experimental step. AC input passes through the PFC and is converted to DC voltage. The DAP converter performs boost and buck operation to control the final output voltage through the OBC's output resistive load. Key waveform of the PFC and DAC converter are overseen using an oscilloscope. The control block diagram of the converter and inverter is as follows. It basically consists of voltage control and current PI controllers configuration in a dual loop. Anti-wind up is included in the current loop to prevent integration situation, and feedforward is added. The feedforward is designed following the given formula and gain setting are adjusted via pole zero cancellation. These are the PFC output waveforms. The converter receives 110 volt AC input and produces 200 volt DC output with a power factor of 0.993 and THD of 6.5%, demonstrating a high level of performance. Voltage level is 7.1% and current level is 3.5%, delivering a stable 20 volt output. During inverter operation in reverse mode, THD dropped significantly from 8.6% using only an L filter to 2.3% when using an LC filter. This section describes the DAC converter hardware and controller design to maximize the GBS legend. The transformer turn ratio is designed as 1.11 considering input and output voltage ratio. The inductor is independently placed outside the DAP to enhance control, efficiency, and reliability. Snapback capacitor minimizes leaning voltage. Circuit parameters are shown in the table. A PI controller is designed for output voltage regulation using paired shift between the primary and secondary H bridge for SPS control. Next is the SPS control result of the DAP converter. The two photos show simulation and experimental waveform when the output voltage is controlled at 150 volt. The following video demonstrated real-time output voltage control from 150 volt to 210 volt in 10 volt increments. Next are the results related to soft switching. The first photo shows the transformer winding ratio set at 1.11 to maximize the GBS operational region, indicated by the shaded area. The second and third photo shows that minimize and maximize phase shift were determined considering the output voltage and power to maximize the GBS area. The two photos below capture GBS operation confirmation at Q1 and Q3 on the primary side, demonstrating reduced switching loss and improved power conversion efficiency. Next are the MOSFETs used in topology. The SiC MOSFET has a reverse recovery charge of about 125 nanocoulomb, which is significantly lower than 3600 nanocoulomb of SK MOSFET, greatly reducing conduction loss. Many SiC MOSFET also provide a Kelvin source pin to separate the gate drive return, minimizing parasite inductance, enhancing switch speed and noise immunity and overall reliability. Thus, the low reverse recovery charge and Kelvin source of SiC MOSFETs contributed to higher efficiency and superior result. Next is the UCC21750 gate driver used in the topology. It used isolated power supply voltage plus 18 volt and minus 6 volt and has no duty cycle limitation. Negative voltage biasing prevents malfunction tunnel case caused by the Miller effect, providing higher efficiency and noise immunity than bootstrap drivers. The automatic reset function linked to PWM input ensures stable recovery after fault. The Miller camp connected directly to the gate suppressed undesired turn-on, and the soft turn-off function gradually lower gate voltage during short circuit or overcurrent, reducing voltage overshoot and device stress, enhancing system reliability. As shown in the right photo, the bootstrap voltage dropped unstably, whereas the isolated power supply maintained stable plus 680 voltage minus 6 volt operation. There were circuit improvements and component replacement for more precise control. On the left, the circuit sensor section was improved by configuring a differential amplifier circuit with an OP-amp that fully utilized the ADC input range of the DSP volt and replacing the sensor to broaden up range. On the right, the voltage sensor section was replaced for precise DC voltage sensing, addressing gain error and nonlinearity with a new voltage sensor, having built-in gain calibration and high-resolution feedback. An op-amp was added and a digital low-pass filter with a 10 kHz cutoff frequency was designed to minimize noise from fluctuating ADC reading. These are the overall waveform of the OBC, key waveform of the PFC input voltage and current, and the DAC converter's primary and secondary voltage and inductor current corresponding to output current are shown. The following video verifies that the final OBC output voltage is well controlled from 150 volt and 210 volt. Next is the efficiency analysis by stage and total OBC efficiency. For the PFC converter, overall efficiency increases as output power rise since the proportion of fixed loss decreases. The DAC converter shows higher efficiency when using SiC MOSFET, with the highest efficiency at 188 volt, where input-output ratio are equal due to transformer turns ratio consideration. The overall OBC efficiency graph is shown. This study successfully implemented stable and high efficiency single-phase bidirectional OBC and confirmed future expansion for battery charging and V12 functionalities. Finally, these are the references. This concludes my presentation. Thank you.